Today we're going to be adjusting exponential decay the same way we adjusted exponential growth. We're going to throw in some stretches and shrinks and some reflections, and then we're going to look at how it applies to some real life situations. So the first thing we want to do is we want to start with a simple exponential function y equals 1/2 to the x power. Now, when we graphed these in the last lesson, we remember that we start, because a is 1, we start at y equals 1, because when x is 0, 1/2 to the 0 power equals 1, and 1 times 1 is 1. Then as we go to the right, we know that we multiply by 1/2, giving us that decay. And as we go to the left, we divide by 1/2, which is the same as multiplying by 2, going from 1 to 2 to 4 to 8, and so on. So this is what y equals 1/2 to the x power looks like, if we can connect the dots properly. There we go. Now, we're going to apply some stretches and shrinks to this, just like we did to our growth functions. So the next one we want to graph is y equals 3 times 1/2 to the x. So you notice that now our a is 3. So when x is 0, 1/2 to the 0 power is 1, and 1 times 3 is 3, which causes this graph to start at y equals 3. But again, since our base is 1/2, as we go to the right, we're going to multiply by 1/2, going from 3 down to 1.5, down to 0.75, and down to 0.375, and so on. As we go to the left, we're dividing by 1/2, which is the same as multiplying by 2, taking us from 3 to 6, and our next point would be 12. So as you can see, this is a vertical stretch of the graph y equals 1/2 to the x. It's as if I took my original function and pulled it upwards. The next one we want to look at is y equals -1/3 times 1/2 to the x. Now our a is -1/3, so that's where our that's where our graph is going to start, at -1/3. Now again, as we go to the right, we're multiplying by 1/2, which is going to take us from -1/3 to 1/6 to 1/12, and so on. As we go to the left, we're dividing by 1/2, or multiplying by 2, taking us from 1/3 to 2/3 to 1 1/3 to 2 2/3 to 5 1/3, and so on. So you see, this graph would be a shrink because our a got smaller, and so it would be a vertical shrink, but it's also a reflection over the x-axis, which is what has us below the x-axis now. So that's basically how we apply the stretches and reflections for our functions. Now, suppose we're given a couple of graphs and we want to write equations and classify them as growth or decay. So let's take a look at a couple of equations that we're given. So we have these graphs. We want to classify them as growth or decay based on the graph, and then we want to find an equation. Now, classifying as growth and decay is simple. We look and see if the graph is increasing or decreasing. Growth is obviously increasing, and decreasing is obviously decay. So, which one of these is growth and which is decay? Well, if you said that A was growth and B was decay, then you're right. So now let's see if we can come up with a function. Well, remember that our general form of our function is y equals a times b to the x, and a is the y value where our graph starts. So if we look at the first graph, our function starts at 10. Then we only need to figure out what we're multiplying by as we go to the right. So what do I have to multiply 10 by to get 12? Well, if you're unsure, just divide 12 by 10. We're multiplying by 1.2. So our equation is 10 times 1.2 to the x power. On the right, we're starting at 8. And what are we multiplying by 8 to get to 4? We multiply by 1/2. And we know that our base had to be between 0 and 1 because we identified this as a decay function. So that works out perfectly. Now, when we were looking at exponential growth, we looked at a growth model that allowed us to look at some real-life situations. With growth, we had 1 plus r. With decay, we have 1 minus r. Now, the 1 always represents the 100% that you start with. And with growth, you're adding an r because you're adding on new growth. With decay, you subtract r because some of what you have is disappearing. So our equation looks similar except for it's 1 minus r, and r is your decay rate, making 1 minus r your decay factor. Now, in example 5 in the book, it says, the number of acres of ponderosa pine forest decreased in the western United States from 1963 to 2002, so there's our range of dates, by 0.5% annually. It's every year. In 1963, there were about 41 million acres of ponderosa pine forest. So we want to write a function that models the number of acres of ponderosa pine forest in the western United States over time. Now, we're going to represent this as P for acres of ponderosa pine in millions. That way I don't have to write out 41 million, I could just put 41. Now, our decay rate that they give us is 0.5%, so I'm doing 1 minus 0.005. Be careful with that decimal, because since it's 0.5%, we need 0.005 to the t power. Simplifying this equation gives me p equals 41 times 0.995 to the t. So there's our equation that represents the number of acres of ponderosa pine forest over time between 1963 and 2002, where t is years since 1963. Now B wants to know to the nearest tenth about how many million acres of ponderosa pine forest were there in 2002. Well, we need to know what time value to plug in. So what's 2002 minus 1963? That will tell us how many years since 1963. The result is 39. So we're going to plug into our calculator p equals 41 times 0.995 to the 39th power. And we're going to round that to the nearest tenth. When we do that out, we get 33.7 million acres of ponderosa pine left in 2002. So all we have to do is plug our information into our equation where they go. All right, I'm going to give you one graph to practice before we quit. So why don't you give this equation a try? Graph y equals 5 times 0.4 to the x, and tell me what the domain and range is, and whether it's a shrink, a stretch, and whether or not there's a reflection. All right, let's take a look. Our A is 5, so that's where we should be starting. As we move to the right, we're multiplying by 0.4. So 5 times 0.4 is 2. So our next point is 2. And then 2 times 0.4 is 0.8. 0.8 times 0.4 is 0.32. And so on. Dividing by 4 is the same as multiplying by 5 over 2, gives us 25 over 2, or 12 over 5. So we've got a rather high point up there that we can't reach. So let's connect these dots. Oops. And there we go. Now normally our graph starts at 1 and decreases and increases from there. So this is a stretch, a vertical stretch of y equals 0.4 to the x, and there's no reflection going on. Our domain, as we've usually seen, is all real numbers. And our range, again, since we can't hit 0, is all positive real numbers. All right, so if you have any questions, feel free to ask. If not, you can move on to your homework.